it's Anna. I am here ready to go over the rest of 3.4. So these are notes for section 3.4. I included the previous notes from 3.4 to kind of briefly refresh our memories and look at what we had worked on before spring break and before extended spring break and before who knows what else might possibly happen. So what I've done here is I've included the notes that I've filled out and have actually also already been posted on Blackboard so that you can kind of refresh our memories and see what's going on. So just a reminder, we were looking at the zeros of polynomials, and we had used this rational zero theorem to kind of test all the different possible zeros for a polynomial. Then we were using synthetic division to find a zero. Here is an example of that, where we tested some zeros until we found a good one. Remember, I had said I wasn't going to give you anything too crazy. Don't try the weird ones, but you might not want to start just only trying the one. But we talked about how once you find a zero, you can rewrite the polynomial broken down by taking out that zero factor and then using the synthetic division to find the remaining factor, and then we use the quadratic formula or other methods like factoring to find the other roots or zeros of the polynomial. So in this case, for that example that we had for A, we ended up getting that x was equal to 2, okay? And x was equal to, where was that? 1 plus or minus radical 2, or square root of 2. So we got through talking about when there are irrational roots, which this is an example of irrational roots. And we see that there are 3 zeros for this cubic polynomial, because we have the 0 that is x equals 2, and we have the 0 that is x equals 1 plus square root of 2, and we also have the 0 x equals 1 minus the square root of 2. So we still end up getting 3 zeros. Hopefully this is familiar, and we've been working on our 3.4 homework despite the longer break. And this isn't news to anyone. So now we're going to move on and look at complex roots. What happens when the polynomial doesn't actually hit the x-axis, but there it does result in like those turning points within the polynomial. And so before we left on that Wednesday evening, we discussed what it means for something to be a complex number. I is equal to the square root of -1. We evaluated some expressions and figured out that we might have to simplify some radicals and pull out an I when we have square root of negative numbers. We did this example, I hope you recall. We ended up finding all the zeros. Remember, we used the rational root theorem or rational zero theorem to find all the possible roots. We used synthetic division to find one root. We found the resulting polynomial, and then we used quadratic formula to solve this to get the 3 zeros. Okay, so hopefully you recall that and have that written down in your notes. Then we get to this very, 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 very important property of zeros, that a polynomial of degree n has exactly n zeros. That's possibly counted multiple times, so we could have zeros that have multiplicity higher than 1. And it tells us that if a plus bi is a 0, its conjugate, a minus bi, is also a 0. Okay, so we're going to see some examples where this is super important. Okay, before we move on to that though, we're going to take a look-see. I'm going to do some erasing, some marking marks. I'm going to take this and shift it up. Just, ooh, hi, sorry. We're going to erase these. And we're going to look at this example where they tell us find a polynomial f of x of degree 3 with real coefficients and the following zeros. So they tell us the zeros. So now remember, when we get the zeros, those are telling us our factors, because our factors are going to be x minus c. So in this case, our c's are -3, 1, and 2. So that gives us our factors. So our factors are going to be x minus -3, which is the same thing as having x plus 3, x minus 1, and x minus 2 equals. There we go. So this polynomial represents exactly what they're saying there. Now, in general, we can actually assume that this has an unknown coefficient in front of it. But we can only find that unknown coefficient if we're given more information about the polynomial. So we're about to see an example that's just like that. Okay, so pointer, boom. All right, so before we see that example, though, I want to make sure that we feel good about working with complex numbers. We have a little note right here to remember that I squared is equal to -1. And so the first thing we're going to do is we're going to multiply these expressions out. So let's do this one. So we're going to FOIL or distribute these two binomials. We're going to get x squared from that, and then we're going to get plus 3ix from that. Then from here we're going to get minus 3ix, and then from here we're going to get minus 9I squared. But I squared is the same thing as -1, so this is going to be the same as -9 times -1, which gives me a plus 9. Okay, these two here, plus 3ix minus 3ix, if you do that, those cancel out to 0, so all I'm left with for this one is x squared plus 9. Okay, so for the second one, it's a little bit more complex because you have more terms that you're multiplying together, but we still want to be methodical about it. We're going to do x times x and get x squared, and then x times -2, so that gives me -2x. And then we have x times -4i, so I'm going to have -4ix. Okay, then I'm going to do this next term times all three of these. I'm going to show it like this, so I'm going to get -2x, so I'm going to put that underneath here. Okay, because these are kind of in the same, they're like terms, okay? So then I'm going to do -2 times -2, which is going to be plus 4, okay? And then we're going to do -2 times -4i. So that's going to give us positive 8i, okay? Then we're going to do this last term here times each of these. So I'm going to get 4i times x, which is going to be plus 4ix. Notice something cool that's about to happen there. Then we get 4i times -2, which gives me, what does it give me? -8i. Okay, and then we get 4i times -4i, which gives me -16i squared. So let's see all the things that cancel. So anytime I have opposites added together, they cancel. So here, negative 4ix plus 4ix, that cancels. Here, I have plus 8i minus 8i, that would cancel. And then remember that here, this is negative 1. So negative 16 times negative 1 gives us technically a positive 16. So now I can combine my like terms that remain, and I'm going to end up with x squared minus 4x plus 20. Yay. Okay, so that's a little, how do I multiply expressions with complex numbers in their review. Notice how when we multiply these out, what happens to our complex numbers? They go away. But if I were to take this, and I would use the quadratic formula to solve it, I would get back to getting that x is equal to these. Okay? So, now let's use this information to do the rest of these problems. We're going to find a polynomial f of x of degree 3 with coefficients, real coefficients, and the following zeros. Okay, I added in this information. I want to make sure we know that f of 1 equals negative 156. So what that means is that's going to help us find our leading coefficient. Okay, that helps us find that a value. Okay, so we know that they tell us our zeros are negative 2 and 5i. But please, please, please recall that if 5i is a 0, then negative 5i is also a 0. So I rewrote these to indicate that I have all 3 of my zeros. Okay? Remember, it has degree 3. There's no added multiplicity on either of those. And so my complex zeros must include both the positive and the negative. So that gives us the following factors. X plus 2, x plus 5i, and x minus 5i. But remember, we have a leading coefficient that we don't know that we're going to have to solve for. Okay? Based on our previous example, we can probably go straight from here to say that when I multiply this out, we're going to get x squared plus 25. If you don't believe me, do it on your own and figure that out. But it is true, so just trust me. Okay? But then they tell us that f of 1 is equal to negative 156. So I can replace all my x values with 1 and replace my f of 1 with negative 156. So negative 156 equals a times 1 plus 2, okay, times 1 squared plus 25. Well, 1 squared plus 25 is 26, and 1 plus 2 is 3. So I'm going to get a times 3 times 26 equals negative 156. Okay, 3 times 26 is, 78? So if I take negative 156 and divide by 78, or I could just divide by 3 times 26, do the same thing on the other side, run out of space, we get that a is equal to negative 2. Okay? Therefore, now I can have the exact polynomial, not just any polynomial. I didn't find a polynomial, I found the polynomial that has 3 zeros. Here are the zeros, and is evaluated at negative 156 when x is equal to 1. So, if there's a problem that asks for the exact polynomial and they give you an f of 1 or f of 0 or f of 10 or f of whatever value, this is the process that you would use to then solve for what is that leading coefficient. Okay, so Now we have a problem that looks very similar. We have find a polynomial, f of x of degree 4, with real coefficients in the following zeros. They tell us that we have the 0, 1, which has a multiplicity of 2, and we have 3 minus I as a 0. So we know that if the polynomial has a 0 that's 1 that has a multiplicity of 2, then that factor is going to be x minus 1 squared, because that tells us that multiplicity of it. Then remember, for our factors of x, we get x minus c. But in this case, we're going to have to use 3 minus I and 3 plus I. Okay? So that will give us our factors f of x for this 4th degree polynomial being x minus 1 squared times x minus 3 minus I times, I'm going to have to write tiny, x minus 3 plus I. Now this hopefully should be sufficient. I believe in my math lab it will take this. If not, you'll have to multiply it out. But remember, when we multiply these two things together, some funky stuff happens and some things go away. And then you can multiply what you get from that times whatever you get from x minus 1 squared. I'm going to stop this video right now. I'm going to make a separate video doing the Descartes rule of signs. So please make sure you watch that. This is getting a little long and I want to cut that one down short. I feel like I can get that one down within about 2 to 3 minutes. So thank you guys. Email me if you have questions. If you're working on your homework and you have questions, check me out on that Blackboard Collaborate. Please make sure if you need help, you get help. All right? Thank you.